Welcome back to our course. In Module 1, we laid the foundations from the logic of econometrics to the mechanics of ordinary least squares, the assumptions it relies on, and what happens when those assumptions fail. In this second module, we will step into more powerful and flexible estimation techniques, the ones you often see in advanced research papers, policy reports, and professional data analysis. We'll explore extremum estimation and why it generalizes many estimation methods. Numeric optimization methods, how computers actually find the estimates. Maximum likelihood estimation, one of the most important approaches in modern econometrics. The generalized method of moments, a flexible framework for estimation. Instrumental variables in advanced settings. Some brief introductions to Bayesian and nonparametric methods. This is where econometrics moves from drawing a straight line to handling more complex, realistic, and messy situations. 1. Extremum estimation, the big umbrella. Let's start with something abstract but incredibly powerful, extremum estimation. The term might sound intimidating, but the idea is simple. Instead of estimating parameters with a fixed formula, we define a function that measures how well a particular set of parameters fits the data, and then we choose the parameters that maximize or minimize that function. For example, in OLS, we minimize the average squared prediction errors. In maximum likelihood, we maximize the likelihood of observing our data. In generalized method of moments, we minimize the discrepancy between model-implied conditions and what we see in the data. Why it matters? This framework is incredibly flexible. Almost any estimation method you've heard of can be expressed as an extremum estimator. Key properties of extremum estimators. Consistency, as the sample size grows, the estimator converges to the true value of the parameter. Asymptotic normality, in large samples, the distribution of the estimator looks like a normal, bell-shaped curve, allowing us to do inference. Efficiency, among estimators that are consistent, some have smaller variability. Extremum estimators can often be designed to be as efficient as possible. 2. Numerical optimization methods. Once we define the function to maximize or minimize, the challenge is, how do we actually find the best values? For simple OLS, we can solve it directly. But for complex models, there's no closed-form answer, we need iterative numerical optimization. Common methods. Grid search, try out a range of parameter values, calculate the function for each, and pick the best. Simple, but slow. Gradient-based methods, use the slope of the function to move quickly toward the optimum. Very fast when the function is smooth. Global optimizers, useful when the function has many peaks and valleys. These algorithms search more broadly to avoid getting stuck in the wrong place. In practice, software packages like R, Stata, Python, or MATLAB handle these optimizations behind the scenes. As an applied researcher, your main job is to set up the estimation problem correctly and interpret the results wisely. 3. Maximum likelihood estimation, MLE. Now we get to one of the cornerstones of modern statistics, maximum likelihood estimation. Basic idea. Imagine you have a model that describes how the data might have been generated. The likelihood is a number that tells you how probable it is to observe your actual data, given a specific set of parameter values. MLE chooses the parameter values that make your data most probable under the model. Why it's powerful? It's flexible, works for linear, nonlinear, and even discrete choice models. It provides a systematic way to incorporate assumptions about the data's distribution. Under certain conditions, MLE produces estimators that are consistent, efficient, and normally distributed for large samples. Key features of MLE. Cramér bound, a theoretical minimum for how much variability any unbiased estimator can have. MLE often reaches this bound in large samples. Likelihood ratio test, a method to test hypotheses by comparing the fit of two models, one with restrictions and one without. Applications, everything from estimating the probability of loan default, to fitting logistic regression models, to building time series models like ARIMA. 4. Generalized method of moments, GMM. GMM is another big step forward. Instead of starting with a probability distribution, GMM starts with moment conditions, mathematical expectations that should hold if the model is correct. For example, in OLS, The errors should be uncorrelated with the regressors. Why GMM matters. It's highly flexible, you don't have to fully specify the distribution of the data. It handles situations with more conditions than parameters, choosing the parameters that make the conditions as close to true as possible. It's widely used in finance, macroeconomics, and development economics. Optimal two-stage GMM. GMM can be done in 2 steps. Use a first guess to get initial parameter estimates and measure the variability in the moment conditions. Use that variability to weigh the conditions in a way that makes the estimator as efficient as possible. 5. Advanced instrumental variables. In Module 1, we introduced instrumental variables, 4, as a way to handle endogeneity. In advanced applications, instruments may come from natural experiments, events that mimic random assignment. Over-identification tests can be used to check whether the instruments are valid. GMM can be used as a more general framework for fall estimation. 6. Additional topics, if time allows. While our main focus is on classical and semi-classical methods, it's worth mentioning 2 more areas that are increasingly important. A. Bayesian methods. Instead of focusing only on the data, Bayesian analysis combines data with prior beliefs to produce a posterior distribution for the parameters. This approach is especially useful when data are scarce or noisy, or when expert opinion is valuable. B. Non-parametric methods. These make fewer assumptions about the exact functional form of the relationship between variables. They are flexible but require more data to achieve the same level of precision. 7. Concluding remarks. We've now covered the general extremum estimation framework, how optimization works in practice, maximum likelihood estimation and its strengths, the generalized method of moment and its flexibility, more advanced uses of instrumental variables, a glimpse into Bayesian and non-parametric approaches. By combining the fundamentals from Module 1 with the advanced techniques from Module 2, you now have a comprehensive toolkit for quantitative analysis in economics, finance, and other social sciences.